In this video, I am going to show how to preprocess data in MZmine. The first thing I am going to do is to edit the file start MZmine windows. And I will change the memory that the program is going to use. And also I will make sure that the R paths are correct, because now MZmine is using R for many functions, for example, LC-MS data peak detection or baseline correction. And now I can start the program. Now I will open the raw data files. MZmine can open CDF files like in this case, but also many other formats. Once the files are open, I can visualize them. For example, showing the total ion chromatogram. With this visualization, we can see, for example, if there are differences in between the samples, like in this case, sample number 3, or if there is a shift in the retention time, like in the sample number 4. Also, if I do double click in the top of one peak, I can see the spectra. Okay. It is very useful to see the 2D plot, where in the y-axis is the mass to charge and the x-axis the retention time, and then we can see, for example, the duration of the peaks, and if we zoom in one peak and do zoom, we can see, for example, what is the maximum difference in the mass to charge ratio between the scans. Now I will do the peak detection. The peak detection is done in 3 steps. The first step is the mass detection. The mass detection module generates a list of masses for each scan in the raw data file. There are many algorithms to do the mass detection, but in this case I am going to use the algorithm centroid because my data is already centroid. So the only thing it is going to do is to remove the noise. I can pre-visualize the data to choose the right parameter, and okay, I see that 15 is okay. Now the second step for the peak detection is the chromatogram builder. The chromatogram builder takes the list of masses generated in the previous step and builds a chromatogram for each mass that can be detected continuously over the scans. So the first parameter is the name of the result of the previous step. The second parameter is the minimum time span, so it should be as big as the shorter peak that we want to detect. The minimum height and the mass to charge tolerance. Now we have the chromatogram build, and we can see that in some cases, like in this case, there are more than one peak in the same chromatogram. For that reason, we need to do the chromatogram deconvolution. And this is the third step. Again, there are many algorithms, including this wavelet algorithm from LC-MS, but I am going to choose local minimum search because it is very fast. Local minimum search is an algorithm suitable for datasets that have very little noise, and what it is doing is searching for the local minima and considering everything that is between two local minima as a peak. So the first parameter is only noise removal, and in this case it will remove 65% of the less intense peak. The second parameter is the minimum retention time range. Third is the minimum relative height with respect to the top data point in the chromatogram. The third is the minimum absolute height, and this is the ratio top peak edge, and it will help to reduce the detection of false peaks in case that the chromatogram is not very smooth. And the last parameter is the peak duration. We can show also the preview to see how the peak detection is performing. Okay. And once we have the detected peaks, I can do the isotopic group. So the first parameter is mass to charge tolerance, second is retention time tolerance, then if my peak is monotonic or not, and the lowest mass to charge ratio is the representative isotope. Now after the isotope grouping, I can, for example, do some filtering to remove some noise, and in this case I will remove all the peaks that contain less than one isotope. This is the result of the peak detection. We get a least peak, and the next step is the identification. For the identification, I am going to use an in-house database, so I will use this custom database search. And it is a file, a CSV file that has to contain 5 columns: ID, mass to charge ratio, retention time, identity, and formula. Then you have to give the mass to charge tolerance and retention time tolerance. And this is the final. This list has been created using MZmine, and we can see that many of the peaks are still unknown. So I will show the online identification in this compound, for example. Search. Okay. I will search in lipid maps because these samples are lipid extractions, and I will show only 10 results. And it is here giving the result. So I can choose one of the results and add it, and now it is here. I want to say that there are many other options. For example, I can search for an ADAX. In this case, the user can also import their own list of ADAX, but there are also here some that it can be selected. And let's see if yeah, it has found one ADAX here. And after the identification, the next step is the alignment. And for the alignment, we have two algorithms. One is the basic join aligner, and the other is an extension of this alignment. It is able to correct the retention time shift. I will use Transact because we saw in the total ion chromatogram visualization that there was a shift in the retention time for the sample number 4. So the first parameter is the mass to charge tolerance. The second is the retention time tolerance. It has to be as big as the maximum shift in the retention time. In this case, it has to be quite big. Also, the retention time tolerance after correction, it has to be quite small. And then runs iterations, minimum number of points. It represents the minimum number of points that have to be included in the model to be considered valid, so it can be estimated by seeing how many peaks the samples have in common. And the final parameter is the threshold value that Transact will use to include the points into the model. So we can pre-visualize, and we can see that the model that Transact is going to use is quite linear, so we can select also this linear model. And this is the result of the alignment. We can, after the alignment, we can filter the data again by removing, for example, the rows that contain less than 2 peaks. Now we open the filter list, and there are less peaks, but we still see that there are many gaps. For that reason, I am going to use the gap filling module. So the first parameter is the intensity tolerance, and it is the maximum allowed deviation. The second parameter is the mass to charge tolerance, and the third is the retention time tolerance. I will do the retention time correction because there was a shift. And here is the list with the gap filling. So I can show, for example, if the gap filling was correct. I can see. Okay. There are still some gaps. Okay. And that's it. After the gap filling, we can, for example, check if the data is correct by checking the coefficient of variation or the PCA. To see the PCA, first I am going to set the sample parameters. Oop. And then I will set values. Control. Case. Add parameter. Okay. No. And then I will put control case. And now I can see the PCA, and I will color by group. So also we can do some clustering or heat map if we want. MZmine has many other functions, for example for normalization and for MZMS peak detection. Also, MZmine contains the batch mode, where you can, for example, select the raw data files and then define here the algorithms that you want to run. And for example, I will put the gap filling, and then I will run. And here we have the peak list again. So after the peak list is ready, we can export it in export, import, export CSV file, and we can select the fields that we want to see. For example, here name and identification method, and the peak list is imported. So that's it. Now we can save the project. Example MZmine.